We are Fc42 and this is our final project presentation for the CS6440 T project. Our project is the Opioid Crisis Management Dashboard. Listed here are all team members and mentors of the project. We'll start with our goals and research, followed by an actual demo of the dashboard. Lastly, we'll cover our accomplishments and overall state of things.
In the past few weeks, we achieved 3 project goals that our outside mentors and we agreed on. First, we identified the data elements relevant to the opioid epidemic warfare. Second, we determined the data representations that are both informative and yet not too granular for sharing. Third, we built an interactive dashboard for researchers to gather near real-time statistics. The dashboard is expandable with other sources to generate more robust insights.
As described in the design, one of the backend components of our OCMD app is the data retrieval from a file server. This is achieved with our Java program File app that is built upon Happy3. The basic workflow is that the File app takes the opioid-related code as input, retrieves the corresponding EHR records from the file server. For our prototype, we're using the Mimic server. It saves the query results into intermediate files and then load them into the backend data store. Separating the query from the data store update is just a practical choice to handle the slow speed in the Mimic server. The next couple slides will explain these steps in more details. Previously, we have discussed what file resources are relevant according to the CDC guideline. Here are the finalized resources based on their availability in the Mimic server. The File app queries these resources using the opioid-related code. Here are the final collection of the code, corresponding to the opioid drug prescription, screening, and induced diseases. One unique feature is that the code are organized using an ontology, such that the users can choose the level of granularity to visualize and analyze the rich information available. As some examples, the 2 snapshots illustrate how the ARC norm and the SNOMED code are organized. Finally, these are the examples of the query results that the File app delivers. Typically, each entry contains the query code, the ID of the EHR record, the associated patient info, the timestamp, and the other useful attributes if applicable. The File app can subsequently load the results into the data store, wherein the results are grouped demographically and summarized as counts.
All right, the basic function of the Data Store API is to provide counts to the JavaScript that's running in the browser. It also provides code and filter keys and human-readable strings for the browser to present. One of the side effects of the API is that an analytics program can be used to query our data, and we know the Georgia State folks are gathering data from other sources and using other programs, so this will be a benefit to them. The standard interface is via HTTP. The request is as you might expect to see in a standard URL. Counts are returned as JSON, and on request, the counts can be aggregated if multiple keys are given. Filters based on gender and age ranges are also provided by the Data Store API. We have a series of unit test programs that run curl to query the data. It's in the data store through this API, and this is just a sample showing 2-month queries. One for a length of 12 months and one for a length of 36 months verifies that we're getting the correct number of counts back, and then that we're getting the correct data back. Our deployment strategy hasn't changed much since the last presentation. We still are deploying 4 containers, one for each of our applications. Those will be connected via a logical Docker-provided DNS-supported network. Our one change is that we, instead of having 1 exposed port, we expect to have 2 exposed ports. The user interface is what we expected before, but the Data Store API is going to have to expose a port so that the JavaScript running in the browser can make a query against Data Store and get Data Store counts. We have an optional volume for the Data Store still, and all of this can be launched with Docker Compose, which allows our Georgia State mentors to be able to easily deploy this in their environment.
So this is a demonstration of the final deliverable for the opioid crisis dashboard web application tier. I think this is a unique approach because we tackled the problem like we would be a maybe like a healthcare administrator and kind of tried to embody the needs that they would when trying to look for specific statistics about opioids. So you can see here I've got codes on the left that I can sort on, and then I've got filters for gender and time frame. So we're gonna go in here and select the past 2 years, and I'm gonna pick one of the high-level RX norm codes for ambulatory care use. So as you can see, when I select here, it makes a call to our backend data store, and this is the data represented from the API call from the data store. I can also filter on subclassification, so I'm just going to look on oxycodone now. And we get another line drawn here. You can see down here there's a legend representing the colors of the different lines for what we've selected. Now I'll go look for a SNOMED code. Let's look for this one, drug-related disorders in SNOMED. You can see we have another line representing the SNOMED code that we selected. Now I'd like to filter on some genders, so let's look for just females. So select females, and the data will update to represent just the female population. And lastly, I'll just pick a different time frame that I'd like to see data on. So let's look in the past 30 days instead. And you can see the data updates on selection for the past 30 days. And this is a good tool that healthcare administrators can use to kind of measure the impacts of opioids in their community backed by their data. Thank you.
Project successes has been discussed in previous slides. We have 3 unique elements. First, the interactive dashboard was designed especially for opioid-related codes. Second, for efficiency, we put data from Redis rather than file server. Third, we also used the HCI principles in GUI design. Next, let's talk about the team members' role and the timeline. Detailed contribution is marked on the Gantt chart. Scott, Nick, Yu are developers. Yang and Michael are QA team. Jason is the project manager. We established communication with our mentors and finished the research in D1. We finished the basic design, server preparation, data gathering, UI mockup, development investigation, and use case analysis in D2. We started development and QA in D3. We set up check-ins, set up user interface, data store and data update containers, built data store API, and set up HTTP server in D3. In D4, we continued development and unit testing. We finished the GUI web server integration, visualization polish, container development, and code ontology development. We completed data store and finalized the data store API. Upon finishing up our report in D5, we're ready to hand off this project to our mentors. As shown in the Gantt chart, the project status is green. All project goals agreed on are complete. There's no outstanding item from the current project goals. The future development may include integration with other Georgia State research and data collection efforts. This project may also be expanded beyond a research tool.